our recent work on the inner core scatter. So, and we all know, like our Earth is protected by the magnetic field from the radiation particles. So the geomagnetic field is generated by the optical convection, or we call it the geodynamo. The driving force of the geodynamo is from the crystallization of the inner core. So to study the structure of the inner core from using the seismological waves can help us to understand the evolutionary history of our Earth, also to understand the formation of the geomagnetic field. To study the interior structure of the Earth, like the inner core, the seismic wave is one of the most powerful tools. And here we list the different kind of seismic waves can be used to study the inner core. The first is the transmitted seismic wave goes through the inner core. The second one is two kinds of backscatter energy. One is the PK small IGP, which is the seismic wave bounce back from the inner core boundary. The second is inner core scatter waves. Is the backscatter energy from the small scale heterogeneity within the inner core. The third one is the normal mode. For this study, we will focus on these two kinds of information used to study the structure and motion of the inner core. So the inner core scatter energy was first identified by John Wadali and Paul Worrell, which is another graduate student of Peter Sherrill. And he used the LASA array, which is a very, very great dense array. The aperture is 200 kilometers and is composed of over 300 seismometers. And they used when they checked the beamforming of the seismic record of two nuclear tests, they find anomalous energy here, which follows the PK small IKP. This energy has never been recognized before. To interpret this kind of energy, they use a heterogeneous layer at the uppermost inner core, and then do a forward calculation to fit the inner core scatter waves. And 8 years later, another study, do a comprehensive study to analyze the appearance of PK small IGP and the inner core scatter energy, still using LASA, use the LASA array. What they found is they find there is only a small event can derive the PK small IKP energy, like 14 of the 71 events had PK small IKP energy, but for the inner core scatter waves, most of them can have that kind of signal. Recently, like 2 years ago, there is another study by John Wadali. He realized if we align the seismic wave using antipodal events, if there is an antipodal event, which means when they arrive, the LASA wave almost arrive at the same time, but when we check the seismogram, of course, no. To align them, there is a small adjust to align all the seismic waves together. This tiny shift from each seismogram is the static. The static correction is trying to correct the effect from the velocity anomaly within the mantle and also the crust and also the topography. So let's look at this case. if the inner core come from the antipodal event, which is almost come vertically to the array, if there is some anomaly and the topography, the energy will not arrive at the same time. So when we do the beamforming for this kind of energy, we will find that all this energy come from this direction. Okay. Sorry for that. So when we look at the beamforming for another event from PK small IKP, we can find after we correct the when we apply the static correction, we can move the observation from the energy from PK small IKP from here to its to the location around its prediction. The blue dot is the predict PK small IKP arrival direction. Okay. So there is a two dash circle. So the inside the dash circle indicates the slowness, or the is indicate the slowness. That means the energy grazing the inner core boundary. So that means all the inner core scatter energy should become within this direction. So this large circle indicates the grazing slowness of the outer core, which means the outer core, energy should come from between the two circles, like this one. So here I will introduce our study on the 3D inner core scattering structure. So after we apply the static correction to all the events, we have what we can do is we do the 1D beamforming for the seismogram recorded by LASA for each event. And we may get some energy around the PK small IKP arrival time, and we use a narrow time window, and we do the 2D beamforming within this time window, and we will get this figure. And then the blue dot is the predict arrival slowness of PK little IKP, and the blue dot is our observation. First, we will record the synthetics and also the observation of the PK small IKP energy. The second one, we will use a longer time window to check the appearance of the inner core scatter energy, like here. And also this is for 1D retracing, and we do a 2D beamforming, and we can see a lot of energy here. And if we can see some pattern like this one, we will know the inner core scatter energy is strong for this event. And we summarize all our results looks like here, and we compare with the magnitude and the depth. So for the depth, we don't find a direct relation between the appearance of PK small IKP and ICS with the depth, event depth. Okay, but for the magnitude, there is one thing we need to see is the event should be larger enough to generate enough the energy large enough to the earthquake should be large enough to generate the inner core scattering and also the PK small IKP energy large enough to record it by the LASA. So magnitude of 5.5 is the criteria. So for next time when we check the large arrays, the 5.5 could be a threshold to use, because larger is compared to other array is larger. Okay. So when we compare with another previous study, and we find that for the inner core scattering appearance, we only have one event larger than we just got one more event. But for the PK small IKP, consider we align the phase better than previous study, because for this study, they just directly do the beamforming. They never do the static correction. So this is worse aligned. So they got less events. We got better. We got more events here, and then we plot all our observations on the map and also on this diagram. So this is all the events. The blue stars indicate the nuclear test. So this is the PK small IGPP arrival on its bouncing point. So for here, I want to emphasize this figure. So this figure, the blue dots indicate the predicted slowness of PK small IGPP. And the magenta dots indicate our observation. When we compare them, we find they almost are consistent with each other. The difference is not so big, which means after we apply the static correction for the beamforming, the directions is almost consistent with with the model we used to do the prediction. For this study, we used our RASP91. If you use AK135, that's okay. So that means after static correction, so it's almost good, consistent with the prediction. So the slowness we used in this study, almost okay. And then we check the 2D beamforming for inner core scattering, each event by each event. We got a very interesting pattern. So this is the 8 representative events. So for the top panel, we find most of the energy comes from the northwest direction, and for the lower panel, most of the scatter energy comes from the southeast pattern. And this is almost all the events has a similar pattern. So now we have this pattern. What we think is about, we are wondering, what's this? Well, from this pattern, we want to determine the geographic distribution of the inner core scattering within the inner core. So the directly method we think about is the back projection method. Back projection method is widely used in earthquake source imaging. I think Wei Wang is the expert in this direction. And the other one is the back projection can be used to image the interior structure, especially the lower mantle. People like to use the back projection to study the interior structure using the PK or the PKP precursor using the back projection. Okay, so for here, I will just briefly introduce our approach a little bit different from previous study. So this is one trace of the the 2D stacked 2D stacked seismogram. So this is the red dashed line indicates the predicted arrival time of the PK small IGPP. We know the energy from this point comes from the bouncing point from the inner core. So this is the slowness. This is the lapse time. Lapse time is account from the PK small IGPP. So this is from the 2D slowness. So we know it's a slowness. This is slowness map. This is from the 0 lapse time, and this is the 2D beamforming point. Okay. So for here, there is 2 circles. These 2 circles is the same like the grazing slowness which is from the black dashed line is from the station side. The magenta dashed line is from the source side. And then we look at this circle. This is almost isothermal, like maybe 10 seconds behind the PK small IGPP. And in this circle, we will randomly choose the one point in this circle, and we draw out the seismogram here, and we know this is from some specific 2D slowness on this on the 2D slowness, on the slowness map, and on the left hand. So my next question is what about this one? So it's on the same seismogram, but with even later. Okay, it's it's from deeper of the inner core. Okay, so it's from the deeper. So when we calculate arrival time, we use the 1D retracing. So what we do is we directly get a one-time window, and we use the center to as its representative arrival time. Okay, and when we just do the back project this energy back to its co-located location with the inner core. And we do this one for each time window, for each event, and each notice. And we have the energy at each point within the inner core. And we normalize by its heating account. And then we will get our inner core scattering map. So the black triangle is the location of Lhasa, and also this black solid line indicates this black line is the separation from the hemispherical or the east and west hemispherical, or the separation of the east and west hemisphere. And from these two maps, we can identify the pattern. The most strong scattering region is from the northwest and also the southeast. And these two regions the depth extension of these two regions is a little bit different. For the northwest one is go as deep as 300 kilometers, and the other one go 400 kilometers. And now we want to explore what could be cause this large scale pattern of the scattering distribution. The first one, of course, the small scale topography of the inner core boundary, that could be a contribution. The second one is the partial melting. Because the inner core is crystallized from the outer core, that could be some partial melting could be also exist, and also this could be also a candidate. The third one is the composition of variant. There are some light elements with the inner core, especially nickel and iron. There are some carbon, the sulfur also could be cause some of the small heterogeneities. But for the large scale variation of the inner core scattering, we think the temperature could be the best and the most straightforward explanation. That's I will tell you why. The first one, we compare the location of the strong weak and the strong scattering region with the tomography model of the mantle. We can see the two strong scattering regions, the blue line, are co-located with the high shear wave velocity zone at the CMB, and the weak scattering region is co-located with the low shear wave velocity zone. And one explanation for the shear wave, the low shear wave velocity zone is it has a high temperature. Because it has a high temperature, it will have a low heat flux, because the heat flux is proportional to the gradient of the temperature. So there is a two low heat flux region, and derived from this boundary condition, the geodynamics will use this as a boundary condition to generate the geodynamo, and then we will get the heat flux at the inner core boundary. So at the same time, this is the heat flux. So the heat flux is proportional to the velocity to the temperature gradient. So the high heat flux corresponding to the low temperature, and the low heat flux is co-located to the high temperature. So when we go back, so this region, strong scattering region, these two regions are co-located to the high temperature inner core boundary, and the low scattering region co-located to the low temperature inner core boundary. So, and then we will propose our physical mechanism is because of the cold region. The crystallization here is fast. Because it's fast, it will generate small grain size and the random alignment of the crystals. So this behavior is tend to generate strong scattering. Okay. So for the second one is for the warm region, it's snow freezing. So it's relatively generate large grain size and tend to generate weak scattering. So this is the most, I'm not sure this is, I don't want to tell you this is the only region, but I think this is the best and the most straightforward region, a reason for the distribution of the scattering within the inner core. Okay, so based on this one, we propose our model like this one. So this from the mantle almost have a degree 2 velocity structure. Two patterns of the low shear wave velocity, one is beneath Africa, the other is beneath Pacific. And there are two cold regions, one is from the South America, the other is from the Asia Pacific. So corresponding to this pattern, we find that the inner core could also be degree 2 structure. We have identified these three ones, two cold regions and one warm region. The cold region has the two, but we have no chance because the data coverage we cannot observe this one. But this is our conceptual model. So this is well studied from the inner core hemispherical dichotomy structure. So which means the eastern hemisphere and the western hemisphere is different. So for here, we don't want to emphasize the inner core should be degree 2. We think that there could be some degree 2 structure superimposed on the degree 1 structure, because the degree 1 is from the velocity, from the anisotropy and the attenuation. For our study, we emphasize the scattering is another physical parameter. So we think there could be some higher order structure superimposed on the hemispherical dichotomy structure as the previous study proposed. Okay, so this is the take-home message of the first one, the first part of the study. The second one, so as we have now the location of the scatterings within the inner core, can we use these scatterings as a proxy to study the inner core motion? Of course, yes. So the inner core superrotation has been proposed almost 25 years ago. The first seismological study is conducted by Xiaodong Song and Paul Richard. The basic idea is they align the PKP BC and the AB. The BC AP is the seismic wave transmit out core, but not inner core. They align these two seismic phase. We find they almost align with each other. But when we compare with the DF is the seismic wave transmit the inner core. There seems a systematically change from the DF. To interpret this systematically change, they require the inner core should be superrotate with 1 degree per year. Almost like 4 years ago, this study is conducted by our Swift, it's by Gabby and Guy. They use the normal mode, they use the split function of the normal mode after correct the mental effect. They find the split function, if the inner core superrotates, so the split function should has also a move. So to constrain this move from different mode, we find the inner core is almost marginally superrotate, but with almost no, but it's marginal as a superrotates. The third one is from the backscattering study. The backscattering study is because there is one pair of explosion events which is almost co-located with each other, and they are 3 years apart. during these 3 years, let's see what happens. The first, let's assume the inner core super rotates. Okay, if the inner core super rotates, so the particle move from here to here, which come closer to the source and the station plane, makes the travel time shorter and the arrival time shorter. And if the let's look at the west side, if the particles move to east side, the repass become longer, so the repass become longer, so the arrival time become longer. So the inner core scatter energy come from the second explosive event will arrive later. So when we plot the arrival time systematically to this plot, we can find the west side almost arrive earlier and the east side almost arrive later. So now, so after they realize this behavior, so they do the same thing. So they do the 2D beamforming and compute the inner core scatter wave arrival time difference from west side and the east side. So this plot they just give the wrong direction. So the east is west and the west is right. So they just have the same pattern as I just proposed, which means the inner core could be super rotate. And the rotation rate is almost 0.15 degree per year. And after and almost 2 years ago, after he applied the static correction, he can identify more robust inner core scatter energy. Like here, this is more consistent. When you compare the 2D beamforming, it looks very similar, and the arrival time difference is a better measure. So use this energy spot. He calls it blobs, and he plots all these blobs back to the inner core surface. And then he can use the 0.07 degree per year to interpret this observation. But the problem is he assumed all the scatters at the inner core boundary, which is our study has proved this is maybe not valid. So we use our back projection to put the energy here to its true. I call it true, but it's maybe not true. Put it to the true location with the inner core and to see what happens. So what we do is we compare the waveforms between the two explosive events, and we just use the seismograms with a high energy and also less difference. That means the cross correlation of the two of the seismogram from two events looks very similar, and we measure the difference. Okay, so this is what we have. This is the measurement from John's paper, 2019. This is the measurement of arrival time difference from our study, almost the same but a little bit different. And the cross correlation should be large enough. For here, I pick 0.9, and the amplitude ratio, which means that the energy from the two, the seismogram from two explosive events should be not change a lot. And this is what we have. You can see some black dots highlight the robust region we use, and we back project all these region back to its inner core location. Use our back projection approach, and then this is the arrival time difference with its location, and this is the show the scatter at this with these steps, and then we do the calculation like if there's an inner core rotate 1 degree, the travel time difference for each of the spots looks like, and compare with the observed shift. So the slope is the rotation amount. So when we compare the result, we find is results show a clear linearity between the prediction and the observation. And the slope is the rotation amount. We find that the rotation amount is almost 0.3, which means 0.1 degree per year. But when we look at this one, we find an interesting part is for this red dot, which is the deep scatters, is almost systematically smaller than the observation is small, is systematically smaller than the prediction. What this comes from? I will talk it later. So I will talk it later. So for here, I want to introduce another concept. So the inner core is within the liquid outer core. It's a gravitational coupling. It is a hold by the liquid outer core from the gravitational coupling between the coupling from the mental anomaly, density anomaly here. And when we check the shear wave velocity of these two problems, it's not symmetric, which means the inner core, if the inner core is free to rotate, the rotation axis may not be the same as the inner core rotation axis. For the previous study, they all assume the inner core rotation axis is the same as the Earth's rotation axis. For here, we want to explore whether the inner core rotation axis is a little bit tilted, like this one. So what we do is we do a grid search. We search the rotation axis together with its rotation amount, and the black star indicates our best result is almost 8 degrees away from the North Pole. However, this is ridiculous because from the geodynamic study, they can allow only at most 1 degree deviation from almost, especially most of the study indicated should be smaller than 0.1. So 8 degrees is too much. So why this comes from? So for here, when we compare the residue of the best fitting rotation axis with the North Pole, we can find one thing. Most of the residue comes from this region. This region is the northwest region of the Lhasa, which is the strong scattering region. When we do this calculation, we assume the single scattering. The scattering strength is strong in this area, the single scattering assumption may not be valid. So multiple scattering could happen. So this is one reason. The second reason is there are several studies report the temporal change of the inner core structure, or maybe some moving of the scatters, and also maybe the topography change. So this will also reported in this region. This could also make some difference make some contribution for the misfit. So when we think about these two effects, so the 8 degree deviation from the Earth's pole is maybe not valid, but our method proposes a promising way to study the inner core rotation axis tilting. So this is the summarized figure for the inner core rotation. Start from the first seismological study from Xiaodong Song. We find the observation of the inner core rotation rate almost converged to 0.1 degree. I still remember when I was a graduate student here, the master mentioned in one seminar. So if we have more and more data, the rotation rate become close to 0. So questions, what's the next step? So next step is what is the relation between the rotation and the inner core scattering? Let's think about one question. So if the inner core is super rotation, which means it's steady faster than the mantle, okay, we have so this is a well-studied global study of the hemispherical dichotomy structure of the inner core, the west and the east side. And when we compare the structure from the equator, we can find one interesting stuff. There is a sharp boundary. Okay. Let's assume the inner core has a circle rotate within 0.1 degree per year. So almost 4,000 a year, it will go one circle, which means it will smell the structure like this one. So this is contradict from different studies. The second one is for our study. So the inner core strong scattering can go as deep as 300 kilometers or 400 kilometers. Also, it will smell out. So what happens? For me personally, I will mostly trust this model. It's the inner core oscillation model, which is firstly I think proposed to interpret this the length of day variation. So why this is happens is it looks like if the inner core is oscillate. Let's consider about the conservation of the angular momentum. If the inner core faster rotation, the mantle will go slow. So the length of day will increase. So if the inner core go west side, the mantle will go faster. So the length of day will decrease. That is why there is observation of the length of day change. And this change has a almost 6-year periodicity. This has been found over 20 years. So the geodynamics try to use the inner core oscillation to explain this signal. This is just one explanation, but it may not be true. But I think this is quite straightforward, and also it's also agree with the guys idea, like if we have a longer and longer observations, it's almost, when we just try to measure the average, it's almost zero. So I think the inner core still has a lot of things to do, like whether the inner core is super rotation, steady super rotation, slow super rotation, oscillation, west side rotation, everything, and also the inner core structure is also has a huge problems. For our study, I think our study is the first to build up 3D structure of the inner core for everything, because for attenuation velocity, there is no way to build an actual 3D structure. So we have developed a way to develop a 3D. So the 3D structure for attenuation, velocity, and anisotropy could be the next step. A lot of effort has put into the seismological study, try to build up the 3D structure. So a lot of things left for the inner core. Thank you for your attendance, and questions are welcome.
Thank you for the excellent talk. I think we can start from questions in the audience initially. Does anyone has any questions? No? No, then maybe we can start from the online audience. So, I see,
sure, I'll ask one. I didn't quite follow all of the pairs that you had where you saw that red-blue, signal that shows that there's differential rotation. But if the oscillation model is right, then you should sometimes see it going the other way, right? So I was going to ask if you see that red-blue pattern reversed at all in some of the pairs.
So which one? So you mean the?
Well, the model that you present at the end, where the inner core is
Oscillation.
It should then sometimes it should sometimes be rotating in the opposite direction. I wonder if you saw that in any of the observations. or if they all are sort of showing it going in the same direction.
For this is a good questions. I have go almost see all the literature review because there's a limited literature for the inner-core moving studies. For the transmitted seismic wave studies, they all think this goes the one way. But the limitation for use transmitted waves is only the repass only go inside the inner core, only a small part. So it could be affected by different kind of effect within the inner core. I think compared to the transmitted wave, the normal mode and the scatter wave had a good average, good and a large spatial coverage of the inner core, which can average such a small, tiny, localized effect. Yes, I really have one case, but only one case to go east side is here. I can. Yes, we have only one case. There are only 3 pairs of nucleation tests within the last working time. The one pair is the time duration of the one is only less than 1 year. That is not so. That is too short. Only 2. This is well documented from 71 to 74. This is another one. So we spend a lot of time and effort on this one, and this is our final result. We don't think it's so strong, but okay. So this is the predicted time shift for 1 degree east side rotation. Okay, this is the This is observed time shift from the LASA, and from this one we know this is consistent and also the same as our observation, which means for the 71 to 74, it's the east side rotation. But for the other one, it's the opposite. This is west side rotation. However, there are some problems. The first one is this signal could be affected by the structure because there is the repass will pass through the subduction, one of the subduction. So this could be a problem for this one. But actually, we got one. This is the only one we got from the west side, and I think it's this is okay.
Okay. Thanks.
Thank you.
So how long was LASA operating for?
6 years, less than 6, almost 5 years. So this is almost from start to the end. And also there is only one period for the 6 year. So our observation is almost like one. You almost occupy a full.
So you just said LASA was operating only for 5 or 6 years.
5 years.
5 years. Shorter than I thought.
Yeah.
So when you look at that periodic signal in the length of day there, there's a lot more going on in length of day than what you've seen there. That's a filtered version, correct?
Sorry?
That's a filtered version of the change in length of day.
Yes.
To uncover the 6-year periodicity that people believe is there. There's a lot more stuff going on in the length of day spectrum, change in length of day spectrum. And I'm wondering how it is that you can rule out that other things in the length of day spectrum might also be affecting the inner core superrotation or subrotation.
Yes, I have done one thing because we actually first we have some prior information that's the length of day has 6-year oscillation. So I play with the filter. I find that the 6-year periodicity is robust within the signal.
That's not my point. I mean, we could argue about whether it's robust, which would be another discussion.
Mhm.
But there's a lot of more stuff going on at other periodicities within the length of day. And
Yes,
there's a lot
yes,
of
yes.
stuff going on in the spectrum.
Yes, yes.
If you look at that, and I'm wondering whether, what it is that makes you sure that it would be just the 6-year thing that you would see in the inner core rotation.
Okay, so from the literature, the major point is the 6-year, the amplitude of 6 years is the strongest. Of course, there is another one like 8.5 year or some else, but 6 years is the strongest. It could be yes or no, but I don't know because I'm not an expert. I just using the data. Yeah, you are right.
Question from the audience? So there's one question online from Eugene. So Eugene, do you want to unmute and ask your question?
On mute.
No, 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 no.
Hi. So,
Always.
okay, I can't see myself, but hope it's not funny. Okay, so just got simple question because I'm not familiar with inner core studies. So my question just be simple. So you propose an hypothesis to explain why the scatters tend to occur in places where the temperature is higher or the temperature gradient higher.
Yes.
You think that's because for higher temperature areas, the grain size in the structure will be larger, creating less scattering. And I was wondering what is that? Why that's the case?
Okay, so there is the thing is first we use the seismic signal. The bandpass of the seismic signal is 123 Hertz, which is sensitive to the scattering scale 1 to 10 kilometer. So within that scattering regime, we think the strong scattering is related to the small scale, and the weak scattering related to the large scale within this regime. This is our hypothesis, and this is from our observation.
Right, but so you have larger grain size in the structure, and you think that will create less scattering.
Yes.
Okay.
This is from the. This is another thing to calculate. This one is there are a study in 2010. They do some synthetic test to put the different grain size in a box, and then calculate the scattering strength from different grain size scale, and they find, as we know, like the inner core has the major component is the iron. Iron within the inner core has the one of the most popular structure is HCP. But if we have some light element, it could be BCP, body-centered BCC, body-centered cubic structure. They test both of this structure, and they find the scatter energy is only related to the scale and only to the grain size, not with the structure. And also, they are proposed like the scattering strength is related to the scale, and the small scale, large, strong scattering, large scale, large scattering. Large scattering, small scale, small or weak scattering, large scale. So within a 1 to 10 kilometer.
I see. Okay, thank you.
Thank you.
I have a follow-up question. So you said that, so I didn't quite understand what's the relation between the temperature at inner core, outer core boundary and the heat flux over there. Can you explain that?
Oh, okay. So,
Or you can pull out your slide if you want.
the slide. No, I wonder if whether it's a chalk. So the easiest way to think about this problem is the article is almost isothermal, almost. Okay, so the temperature here is almost the same. So this is warm, this is cold. So the temperature here is all T0, but for here is T1, this is T2. And as we know, in most part of inner within the Earth, the temperature grow with depth. Okay, so the heat flux is from this direction. Okay, so the temperature here, this one, so this is the T2 is larger than T1. So when we compute the heat flux, so this is small compared to this side.
But what about the outer core, inner core boundary? This is the core mantle boundary.
Yeah. So this is another story. So this is a look at from the geodynamics. It's like the flow comes from this one, go down, take the cold fluid to this region. This region draw some.
Oh, so you mean the convection within the outer core?
Yes. So the cold flow attaches this area to make this area temperature a little bit slow.
Temperature lower.
Lower and compared to this one. So this is give the boundary for here. So there is a temperature attached to the inner core is a little bit different in different areas. Makes the crystallization in this area and this area different.
So the colder area will have a faster crystallization rate.
Yes.
And the cold area on the inner core, outer core boundary corresponds to the warm area at the core mantle boundary.
Yeah.
Okay.
Any other questions? Okay, so then let's give Wei thank you.
Thank you.
We have Jimmy Shumanich from industry, and he will talk to us about geothermal field.